Welcome back to the lecture series on microeconomics. Now we are going to look at the other formulation of production function, and this time we are going to look at the production function in long run. So, in long run both the inputs are variable. So, we are going to now represent production function through a concept known as isoquant. So, when we talk about isoquant, we have to talk about a production function of two variable inputs. So, if we have to represent total product curve, then it is going to be a 3D diagram. So, here I am trying to draw a two variable input production function in a 3-dimensional plane. So, along this z axis I am going to measure the total output q, and we are going to measure variable input x1 along this axis and x2 along that axis. So, I can now assume this law of variable proportion holds. So, in that case, with respect to each input axis we can have the curve moving like this. So, basically this will be f of x2 when x1 is given, and we can also draw a similar diagram for production function from origin with respect to x1 axis this time, and we get f of x1 given x2. So, we can see that it is going to give us a shape like a dome or like a hill, right. So, the height of the hill from the level measures the degree of the volume of output. Now, one can think about a conical cross section of this production hill. So, suppose I fix some value of output at q naught level. So, then basically what I am saying that I have to take a conical cross section, and most likely I am going to get a shape of that cross section. So, if I now superimpose this curve that is just generated in the 2-dimensional input plane, then what do I get? Suppose I take a point here, say point A, and I take a point there, say point B. So, I can take these 2 points A and B on this contour line q naught or isoproduct line q naught, and then I can superimpose these 2 points in the input plane. So, here I can take another conical cross section, and the height along the output axis this time will be q1, at which I am going to take the conical cross section. So, I am going to get another curve like this, and this will give me again like previous one all the input combinations like say C, D, which will produce the same level of output say Q1. So, these generated curves which are superimposed on the input plane are called isoquants. So, now let us have a formal definition of isoquant. Isoquant or isoproduct curve is the locus of all technically efficient production processes What do we mean by production processes? These are basically combination of factor inputs for a given level of output. In a simple word, we can also say that isoquant curve shows all input bundles that produce exactly same level of output. Okay, so now let me have a simple diagram, and this time we are going to draw isoquant in two-dimensional plane. x1, x2 are the variable inputs, and now I am going to draw the curve. Something like this will happen. Some sort of curve like this we are going to expect in the input plane, right. Q naught is basically the given level of output at which the conical cross section of the production hill has been taken. Now, why it is called technically efficient? Because note, take any particular point, say here, okay, let me call this point A. Now, note that this shows a specific input bundle to produce the level of output Q naught, and let me denote this as x1 prime and x2 prime. Note that there are other possible input bundles available which could produce the same level of output. So, for the example, we can consider this point B, where more units of input 1 is given. So, B can also produce the same level of output Q naught, but B is not part of the isoquant. So, that is why it is only giving us the technical efficient input bundles. So, now we do not need B anymore. So, let me remove this. Let me also remove this A and other things, as I do not require. Let me clean this diagram, as I do not require that point A anymore. So, whenever we have a curve in economics, we are also interested in the slope of that curve, and here also the slope of the isoquant has special interpretation. So, let us have a formal definition and derivation of the slope of a isoquant. So, here we can start with the production function Q x1 comma x2, two input production function. We can go for the total differentiation dq, right. Then we can have first partial with respect to input 1 times dx1, we have f2 dx2 similarly, right. Now, this item will become 0 because there is no change in the output value, as we are on the isoquant, and the definition of isoquant says that it is for a particular level of output. So, there is no change in output. So, we get this is the slope of the isoquant, and generally when we write slope, as this is for a specific level of output, we write that as well, say Q equal to Q naught, say, that is more proper. So, now let us make a comment on the slope. So, F1 and F2, these are the marginal products, and we assume that F1 and F2 are both positive. So, we are not in the stage 3 of the neoclassical production function. So, this implies that we have a downward sloping isoquant, and we can abbreviate isoquant as IQ. So, now let us look at a very important concept known as marginal rate of technical substitution. Which is abbreviated by shorthand MRTS. So, MRTS between two inputs is the amount by which the quantity of one input can be reduced when an extra unit of the other input is used in order to produce the same level of output. And now let us going to look at a formal definition of MRTS. As in a 3-stage neoclassical production function, we have a stage where the marginal product becomes negative. Here also we can assume that marginal product can become negative. When we wrote the initial slope of the isoquant, we have assumed that marginal products are positive to have a downward sloping isoquant, but we do not have to assume that. If we assume that we are in the 3rd stage of neoclassical production function, which is anyway pretty unrealistic, but suppose theoretically if we are there, then what is going to be the shape of the isoquant? Now let us have a look at that possibility. So now we are going to go back to the isoquant Q naught, and of course one can have series of isoquants displaying various levels of outputs. So, one can have another isoquant, say Q1 level of output. Okay, we need at least 2 isoquants to tell the story, and when we have series of isoquants, the higher level of isoquants display higher level of output, and that is known as an isoquant map. So, here we have what is known as isoquant map. We would like to end our discussion on the isoquant saying that 2 isoquants cannot cross each other in the isoquant map, and I leave it to you to find out why. So, now let us talk about the possibilities of 0 and negative marginal products, right. So, let us work with this Q naught isoquant and let us have couple of points. So, let me have one point where I can draw a straight line which becomes tangent at that point, and it also becomes parallel to the x2 axis. Let me name this particular point as T1. Okay. Similarly, I am looking for another point along the same isoquant where I can draw a tangent which will become parallel to the x1 axis, and suppose this is the point, and let me name that T2, and we can have some points like T3 and T4. Now, any point such as T3 and T4 are basically inefficient points. Now, consider the point T1. So, at T1 what happens? At T1 the F2, or it implies the marginal product of the input 2 becomes 0, and it becomes negative to the left of T1. Right. So, if that is the case, we see that we have a negative sign in front of the slope, but if one of the marginal product becomes negative, then the slope will become positive, and then we can have upward sloping isoquant, and this is what exactly we are getting. So, the point T4 here actually lies on the positively sloped isoquant, where we see the marginal product of input 2 is negative. Similar explanation could be given for the point T2 as well. So, at T2 the slope of the isoquant is 0, right. So, if the slope of the isoquant 0, then that means F1 becomes 0, of course, and it becomes negative beyond T2. So, we get to see that a point like T3 has negative marginal product. These are theoretical cases, but in reality they are kind of ignored. Similarly, we can find points along the Q1 isoquant as well, where the marginal product of one input becomes 0 at one point of time. So, suppose these two are the points. So, now if we join such points with origin, we get a curve. So, this curve joins all the points along which marginal product of input 2 is 0, and let us have another curve joining the points along which the marginal product of input 1 is 0, and these two curves are known as ridge lines. And economists are basically interested in the area which is bounded by these two ridge lines. So, in traditional economics we are going to study downward sloping isoquant only. We will not have upward sloping segments of the isoquant to rule out the negative marginal productivity of any input. So, we have looked at the slope of the isoquant, and now we assume that we have a downward sloping isoquant, but what about the curvature? Is it convex to origin or is it concave to origin? So, for that also we have to assume certain things, and we have a law which will give us a convex to origin isoquant, and this is what we are going to study next. We have to talk about the behavior of MRTS. That means whether it increases or decreases with respect to one input. Say we are increasing one input x1, then what happens? Now what does this MRTS actually gives? So MRTS basically gives a degree of substitutability. So now let us look at this substitutability issue in greater detail, which will lead us towards the curvature of the isoquant. So again we are going to measure two variable inputs along the axis. Now we will first not draw the curve, we will first start with two input bundles. Suppose we have this initial input bundle A with some coordinates, okay. Now suppose I want to produce the same level of output, but not using the input bundle A. So then I know that the isoquant is downward sloping, and I can have an alternative bundle, say here denoted by B, which also gives me some input combination that will allow me to produce the same level of output. So what happens really? So let me name this intersection point C. So as we move from the input bundle A to B along an isoquant, I have not drawn it, but assume that there is an isoquant, then we employ BC units more of the input 1, and there is a reduction, corresponding reduction in input use 2, and the reduction or the magnitude of reduction in input use in input 2's use is given by the line segment AC. So if that is the case, then productivity of the input 1 decreases because we are utilizing more units of it. If we follow a conventional production function, a concave to origin production function showing the decreasing returns to the variable input. So similarly, as the use of input 2 has gone down, we can expect that the marginal product of input 2 has gone up by following the same logic. So we can write the marginal product at point A is greater than the marginal product at point B, and we can also write if 2, the marginal product of input 2 at A is less than the marginal product at input bundle B. So now let us take ratio. Why we take ratio? Because we need to get down to the form of MRTS. So F1 divided by F2 at input bundle A shall be greater than F1 over F2 at input bundle B. So, this means the MRTS at point A is greater than MRTS at B. So, the absolute value of the slope has increased as we moved along the isoquant from A to B. So, if absolute value of the slope has actually increased, then we can draw an isoquant which gives us this convex shape. So, here is the result. Convexity of isoquants follow from the law of diminishing marginal product. So, we are going to continue with the discussion in the next lecture.